And here's the deal. I brought this up as an introduction so we could see what Ka looks like and stuff like that. But in all likelihood, you may never have to do a calculation like this. You might. There was one in your notes. But you probably won't. What are the more common calculations on this exam? Buffer calculations. This is just simply just a weak acid. That's not a buffer. Just a weak acid all by itself, that's not a buffer. What do you need to actually have a buffer? Got to have minimum 2 things in your solution. What are those 2 things? Weak acid and conjugate base, or weak base and conjugate acid, same diff. So notice, only thing we stuck in our solution was weak acid. That's not a buffer. I would need both weak acid and conjugate base in my solution. And if you have both weak acid and conjugate base in your solution, you just plug your numbers of what concentrations you have right there, and then your Ka's there, and you could solve for H+. And from your H+, you get your pH. It really makes the math a lot simpler. None of that ice table stuff or anything like that. But we often don't even use this equation anymore. We take the negative log of this whole equation and get what famous equation? Henderson-Hasselbalch, sometimes called the David Hasselhoff equation. Take the negative log of that Ka expression, rearrange it a little bit. This is where you get the Henderson-Hasselbalch. Now, sometimes people will write the Henderson-Hasselbalch instead of pKa plus log of A minus over HA, they'll put minus log and flip this over HA over A minus. I'm never going to show it that way. I'm going to do it this one way every time, and I'd recommend you pick one way and do it every time like that as well. If you kind of have both equations in your head, you might flip the plus and the minus or slip up somewhere along the way. This is the most common one presented. It's the only one I'm going to deal with. This is Henderson-Hasselbalch. Here's the deal, though. This can only be used when you have both weak acid and conjugate base in your solution, when you've in some way, shape, or form produced both in there. Notice back in this problem here, what was the only thing we actually stuck in our solution? Weak acid. You can't use Henderson-Hasselbalch in that situation. For just weak acid, you have to use the Ka expression. There's no way around it. Now, for a buffer, you could still use the Ka expression, or you can use Henderson-Hasselbalch. So in a biochem, we just use this much more prevalently for buffers. But keep in mind, it's got its limitations. If you only have a weak acid, you can't use this. If you only have a weak base, you can't use this. This only works when you have both. We are going to, we're going to spend a significant amount of time talking about buffers. So we've talked about now what you need to have a buffer, a weak acid conjugate base, but what is a buffer? What's the point? Stabilizes pH, resists changes in pH. Why is that a good thing? So I heard you say blood. What is somebody over here? Enzymatic reactions, things of this sort. So here's the deal. In your blood, the pH is 7.4. If your pH in your blood drops below 7.35 for a whole lot of time or goes over 7.45 for a whole lot of time, you're in a lot of trouble. Notice that's not a whole lot of change of pH, and you're in a lot of trouble at that point. So your blood needs to be buffered in a very, very narrow range of pH. And that's the way it is for most organisms. Most organisms, there's only a very narrow window of pH that they can live. You know, there's a few exceptions to that, but that's pretty much the general rule. And so organisms are all buffered in some way, shape, or form. What's the buffer in your blood, mostly? Bicarbonate system. Bicarbonate system. It's an equilibrium between carbon dioxide coming in from your lungs and bicarbonate and carbonic acid and all this stuff. So, but that's the buffer in your blood, and it works really well. So I wouldn't test it out or anything. Don't go injecting like HCl in your veins and see, watch my buffers work. It might not work as well as you want. So, but that's the way it works. Really important also for enzymatic reactions. Enzymatic reactions, enzymes, often only work within that narrow range, and that's one of the big things of why organisms need it. So the protein structure, it's pretty much pH dependent. We'll see that if you change the pH a whole lot, your protein might unfold, it might denature, and that's a problem. So as we'll see, your function's dependent upon that. So also in just a regular chemistry context, so the spontaneity and kinetics of a chemical reaction is often dependent upon what the pH is. And since a lot of chemical reactions produce protons or consume protons, so the pH can change wildly so as the reaction proceeds, and that could cause it to slow down or speed up and cause problems either way. So we often buffer chemical reactions as well to prevent that from happening. But buffers are really important. So for a couple of reasons there. before we get into buffers too much, we got to talk about the 3 ways to actually make a buffer. So first off, you can just mix HA and A- together directly. HA and A- together directly. Sweet. Put them in together, awesome. What's the best ratio to put them in at, by the way, for maximum buffering capacity? 1 to 1. When they're 1 to 1, that's when you'll have the greatest buffering capacity. Now, you may have to tweak it away from that ratio to get the right pH you want, but it would have the maximum buffering capacity when it's 1 to 1. So, but that's not the only way to make a buffer. So you can actually just use only weak acid to start and only weak base to start, and then instead of adding the conjugate, just add something strong. And so in this case, I might add any strong base, like say sodium hydroxide. And in this case, I might add any strong acid, say like HCl. And again, any strong base or any strong acid would have worked here. So and the idea is this. HA, here's a weak acid. NaOH is a strong base. What do we know about a strong base? Dissociates completely, meaning it'll react with any acid in your solution 100%. So if I put in 10 moles of HA into the solution and add 5 moles, half as much NaOH, how many moles of HA will be left? 5. The other 5 reacted, but notice what do they turn into? The hydroxide steals the H away, and so the other 5 moles of HA that reacted turned into what? A- and water, but A- being the key. So 5 moles of HA left, but I formed 5 moles of A-. A 1 to 1 ratio of these would be present, just like we did in the first example. So if I'm mixing weak acid conjugate base directly, 1 to 1 gets you your maximum buffering capacity. But if you're mixing weak acid strong base, you want to go with a 2 to 1 ratio to get to that point of maximum buffering capacity. Because if in a 2 to 1 ratio here, you'd end up, when the reaction's over, with a 1 to 1 of weak acid conjugate base. Same thing here with weak base and strong acid. So when my weak base reacts with HCl, what does it turn into? HA. You form some chloride as well, but you form HA, and that's the key. So 10 moles of A- reacting with half as many, 5 moles of HCl, I'd have 5 moles of A- left, and I would have formed 5 moles of HA, and again, that's a buffer. Those are your 3 principal ways of making a buffer. Notice, if you add strong base or strong acid to a weak acid or weak base, what is that often called? And you often use a burette to carry it out and do it in a beaker, and might use an indicator and titration. So a titration. So you can kind of almost think of this as you're titrating the weak acid till it's a buffer. So I briefly want to talk about titration curves and the wealth of information you can get from one. So we look at a titration curve, and here we're going to titrate a weak generic acid that I'm just going to call HA. So I'm titrating this. The only thing I have in my solution first off is HA. So should the pH be high or low? Low. I got an acid, it's HA, so the pH is going to start out low. And what you'll see is that initially when you start adding strong base, the pH jumps up a little bit. And then it kind of flattens out. And then you get a huge jump and flattens back out again. Cool. 2 really important points on this graph. So the first is where it goes almost as vertical as it can go. So that's an inflection point right there. And what do we call that point? That's your equivalence point in the titration. It's where you've added an equivalent amount of hydroxide of whatever strong base you're adding to your acid HA. Notice I said hydroxide. Let's just say this is sodium hydroxide for a minute. The equivalence point would actually mean the point where I've added equivalent number of moles of HA and NaOH. Another way to say that would say that molarity of HA times volume of HA equals molarity of NaOH times volume of NaOH. Notice what's molarity, moles per liter, times liters. Moles. This is the same thing as moles of HA equals moles of NaOH. That's the equivalence point. Notice what's confusing is it's where the moles of HA equals moles of NaOH. A lot of students get confused and they just say, oh, moles of acid equals moles of base. Be careful. I don't want you to say it that way. In this case, it's moles of acid equals moles of strong base. And we'll see why that's important here in a sec. So if that's the equivalence point, if you had half as much volume of NaOH, halfway there, you get to probably a more important point from a biochemistry standpoint. You get halfway to the equivalence point. Halfway to the equivalence point, let's go back and look here for a second. If I started with 10 moles of HA, how many moles of NaOH would you need to get all the way to the equivalence point? 10. For 10 moles of HA, it'd be 10 moles of NaOH. To get to the half equivalence point, how many moles of NaOH, though? Just 5. Ooh, so 10 moles of HA and 5 moles of NaOH, what would that be? It'd be a 2-to-1 ratio, and that would be your buffer. And notice that's where the pH is most stable, where it's not jumping a lot. That's the buffer range in the graph. And so if you've got a titration curve, you can get a couple things here. One, you can kind of figure out, if the pH scale is labeled anyways, what the buffer region is. So, but more importantly, we can get a little more detailed information than just that. But this is the point where the concentration of HA and the concentration of A minus, or the moles of HA and the moles of A minus, are equal. So notice, a lot of students remember the equivalence point that, oh, moles of acid equals moles of base. And then they remember the half equivalence point and they say, moles of acid equals moles of base. And then they get super confused. So notice, at the equivalence point, it's moles of the acid and the moles of the strong base you're titrating with. But at the half equivalence point, we're talking about moles of the acid you're titrating and moles of conjugate base that are equal. Cool. And if you look at your Henderson-Hasselbalch again, so if the concentration of A minus and HA are equal, then what ratio is this? 1. And what's the log of 1? 0. And what would the pH in a generic sense equal at that point? The pKa of your acid. So at this point, HA equals A minus, but as we just learned from Henderson-Hasselbalch, that would also mean that your pH equals your pKa. You can also say that your pOH equals your pKb. We will probably not have to use that, but it's no less true. So, but these two are the things we're going to look at most. HA and A minus, conjugate acid, conjugate base concentrations are equal, and pH equals pKa. So right by looking at the graph, you now know the buffer region, and you know that that corresponds, wherever it hits the pH scale here, that would be the pKa of your acid. So it turns out, and that's where we'd have maximum buffering capacity. So that's the next thing. The pKa of the acid in your acid conjugate base pair, whatever that pKa is, that is the optimal pH for which you could make a buffer using that system. And you get plus or minus 1 on there. So if we were to look at acetic acid, like we did a little bit ago, the pKa of acetic acid was 4.76. What would be the optimal pH of an acetate buffer with an equal amount of acetic acid and acetate ions? 4.76. That's where pH would equal pKa. But what range could it be used over? Awesome. You could use it anywhere from 3.76 up to 5.76. So notice down here would be like 3.76 up to 5.76, but you get outside that range, and the pH starts to jump wildly. It's no longer a buffer. So could I make a buffer of, say, pH 8 using the acetate system? Not at all. Wouldn't work at all. pH 8 is where it's really jumping. Not a good buffer at that range. So not every system can make every buffer. So you may get a question on the test that just lists a bunch of acids and conjugate bases and gives the acids pKa's and says which one can make a buffer of pH whatever. Well, just find the one that's got a pKa within 1 unit of the pH of the buffer you're trying to make. Cool. One other thing to note. If you look at the pH scale, the pH is a logarithmic scale. What's more acidic, a pH of 7 or a pH of 6? pH of 6. How many times more acidic is that? 10 times more acidic. It's a logarithmic scale. There's 10 times more H plus at pH 6 than at pH 7. How much more acidic is pH 5 than pH 7? 100 times. 2 powers of 10. So every pH unit is a power of 10. So 2 pH units, 2 powers of 10. 3 pH units, 3 powers of 10. But it also works like this in the Henderson-Hasselbalch. We can get another thing out of this. So notice if you have equal amounts of, say, acetic acid and sodium acetate, and there's the pKa of acetic acid, what would the pH be? 4.76. Equal amounts, pH equals pKa, and there's the pKa of acetic acid. Be 4.76. But let's say I had 10 times more acid than conjugate base. So this ratio here would be 1/10 in the equation. Well, you can see log of 1/10, and you can plug that into your calculator and find out that means -1 and all that stuff. But let's just think about this logically instead. Your calculator can do wonderful things for you. But conceptually, here's what you want to take home. If you have more acid than base, well, if they were equal, the pH would be 4.76. So if you have more acid than base, should the pH go higher or lower than 4.76? Lower. And the way it works, 10 times more acid, 1 pH unit lower, 3.76. What if I had 10 times more conjugate base than conjugate acid? 1 pH unit higher. What if I had 100 times more HA, acetic acid, than acetate? What would the pH be? 2.76. Would it actually be considered a good buffer? No, but I can still do the calculation. Cool. That's how that works. We'll take advantage of that same kind of a thing later when we start talking about amino acids. And is it in the acid form or the base form? Which one predominates and all that stuff? Same kind of thing. Cool. Biggest thing again from this titration curve, half equivalence point. You can get the pKa and the buffer range of that particular system. Really important. Cool, one other thing. Your buffer. So when do you have maximum buffering capacity again? So, well, again, within that range, that's when you can be a buffer, but when is it at a maximum buffering capacity even within that range? When your pH equals your pKa, i.e. when you have equal amounts of conjugate acid, conjugate base. So one more thing to that, though. You can also get a better maximum buffering capacity, not if these are just 1-to-1, but if they're as high a concentrations as possible. So I want them to be fairly equal in concentration, but I want large concentrations as well. And the larger they are, the greater the buffering capacity. But notice, even if you've got a pretty good buffer, if you add enough acid, eventually you will get out of that buffer range. So every buffer's got a limit to what it can do. But the closer HA and A- are in concentration and the greater their concentrations, so the greater that buffering capacity will be.